Okay, my name is Jordan Harriman, and this is my presentation of artificial blood vessels. Okay, so for an introduction, the purpose was to design and evaluate artificial blood vessels. Now, we did this by choosing 3 different materials and doing research on these materials. And we created 3 different lengths of artery for each of the materials and tested them to determine our objective, balance the physical requirements with the material strength and cost. Now, the artery or the blood vessel that I chose is the aorta that comes off of the heart. So all of my tests will include the 3 different lengths with the 3 different materials, and they all have the same diameter of 25 millimeters, and they are all 3 millimeters thick on the walls of the blood vessel. Now, the methods that I used to do this is material research, SolidWorks design, and the SolidWorks simulations to determine the outcomes and pick a material in the end. Now, for the testing, there were lengths of 1, 10, and 100 millimeters. Now, all 3, like I said, materials have one each of these lengths, all with the same diameter of 25 millimeters and a 3 millimeter thick wall. This reflects the aorta. We used SolidWorks flow simulation. As you can see on the right, those are the results. So this kind of shows like the pressure gradient of the blood moving through the vessel. And you can see all the numbers kind of come out a little bit over, if not at what's considered like a pretty average human blood pressure. This is because the outlet pressure is actually human blood pressure, and the inlet is of 5 times what the normal like resting blood flow rate is for a human. Now, we did this to kind of like stress test the material, and with these pressure values that I took from the pressure gradient, I put them in a SolidWorks force simulation, and I put a pressure force on the outside of the wall, and I ran the simulation to get an easy reading on the strain of each of the different lengths of vessel, depending on what the material was, and I used that to determine my overall decision in the end. Now, for the first material, it's called PTFE. This is a pretty common one. It has excellent biocompatibility, low friction coefficient, which means that the blood doesn't really have like a no slip condition as bad as some of the other materials. Makes it reduced blood clot risk, which I thought was cool. Commonly used in vascular grafts. Like, this is a proven material, and it's approximately $100 per square meter. So for the metal grade, which is also the cheapest material that I have out of the 3. Considerations: it has limited flexibility and rigidity. It can be a drawback for certain applications, and for its durability, it might have like a higher strain, which is something that I also looked into, because for the aorta, it is just a large vein and there's a lot of blood flow going through it. So I didn't really want a whole lot of strain. Now, I couldn't do a strain test on this material in SolidWorks because it wasn't included in the library, and there wasn't really anything that was close to it. So I kind of did hand calculations to kind of determine the rough estimate of what the strain would look like. Now, for material 2, this is called Dacron. It's like a polyethylene. On the right, you can see that I did run a strain simulation on this one, and that the results came out to be very small for the amount of strain. The graph on the right there is showing strain in millimeters. Now, properties of this: it has very high tensile strength and durability, which I thought was super important for this large artery. Applications preferred for larger diameter vessels like the aorta, and strength and longevity, which is important. Now, the cost for this one was a little bit more than the last one, at $150 per square meter, and considerations: kind of minimal strain under pressure, which is like kind of what we were looking for in this application. And the third material is polyurethane. This one has a lot more bend, a lot more strain. It's more malleable than the other 2, and it's also the most expensive. It could exceed over $200 per square meter. Applications is pretty suitable for the flexible areas, and you can see on the left it has much more strain than the previous material, the Dacron. So, kind of looking into this, I didn't figure it was a good material for my certain application. So I moved on with the chosen material here. It's Dacron. A couple of reasons why I chose it: the pressure handling, withstand high internal pressures, which I thought was super important for the aorta. Strain response, low strain. You don't really want to be bending and unbending right off of the pulse of the heart, just for the location. Primary use, ideal for large diameter vessels. Also had a good selling point, and it's not the most expensive. And yeah, that's pretty much it. Now, these are my references. It's a biomaterials website, and that is all. Thank you.